Hi everyone, I am Neil Trevitt. I work on developer ecosystems at NVIDIA and I am president of the Khronos group. And I'm going to give a high-level overview of the new ray tracing capabilities of Vulkan. Vulkan ray tracing is the industry's first open, cross-vendor, cross-platform standard for ray tracing acceleration. It is a set of Vulkan, GLSL, and Spira-V extensions that seamlessly integrate ray tracing into the existing Vulkan rasterization framework. The final versions of the Vulkan ray tracing extensions shipped in November 2020 and are the result of design contributions from multiple hardware vendors and great feedback from the software development community. Vulkan ray tracing can be deployed across many different hardware architectures, including GPU compute, as well as dedicated ray tracing cores. And it's designed for eventual shipment on mobile and embedded GPUs, as well as desktop platforms today. Vulkan ray tracing can be used for both real-time and offline rendering and will be familiar to users of other ray tracing APIs, but it also adds significant new innovations that we will be covering later in this presentation. Vulkan ray tracing enables developers to use today's ray tracing hardware, and it creates an extensible foundation to support new ray tracing techniques as they are developed. Now, creating a cross-platform, future-proof ray tracing framework took significant effort. A Vulkan subgroup was formed in January 2018, and NVIDIA shipped a prototype vendor extension called VK-Ray as a design contribution. In March 2020, Khronos released provisional ray tracing extensions that were quite similar to VK-Ray to gather developer feedback. And that developer feedback led to the final extensions being much easier and more flexible to use and capable of supporting DirectX ray tracing, that's called DXR, as a layer over Vulkan. The final extensions were released in November 2020, together with AMD and NVIDIA shipping conformant drivers and tools to enable developers to use either HLSL or GLSL for their ray tracing shaders. Finally, the Vulkan SDK was updated in December 2020 with ray tracing support and samples to enable developers to easily integrate Vulkan ray tracing into their applications. But before we go into more details, let's answer a basic question. What is ray tracing? Ray tracing is a rendering technique that realistically calculates how light rays intersect and interact with scene geometry, materials, and light sources to generate photorealistic imagery. It is widely used for offline film and production rendering, and now, for the first time, the latest GPUs have enough performance to crunch through an enormous number of ray calculations quickly enough for ray tracing to be used in real-time applications and games. Many rasterization techniques have grown up over the years to approximate how objects look in real life, but only ray tracing accurately calculates physical phenomena such as shadows, reflections, and refractions, making rendered scenes look far more realistic and making them easier for artists to create. The technique of ray tracing has the potential to improve almost every aspect of 3D rendering because the basic idea of calculating how rays intersect with the scene geometry is an extremely flexible tool that can be used by creative developers to accurately render many different types of visual effects, just some of which are shown here. In fact, ray tracing can be used to accelerate tasks other than 3D rendering, for example, calculating how audio propagates through a 3D scene, or simulating how camera, LiDAR, and radar sensors in a self-driving car perceive the world around them. So how do you use Vulkan ray tracing? Like many other ray tracing APIs, the first step is to build all the scene geometry into an efficient two-level acceleration structure so that searching for millions of ray intersections can be performance optimized. The precise internal organization of the Vulkan acceleration structure is opaque to the application so that the hardware vendor can optimize it to match their own architecture. Therefore, Vulkan provides API calls to supply the scene geometry to be built into the structure by the Vulkan driver. The second step is to launch rays into the scene to calculate how those rays intersect and interact with scene geometry, materials, and light sources, and to process those intersections to create rendered images. Vulkan provides two ways to dispatch rays, both with programmable flexibility to enable a wide variety of visual effects. Ray tracing pipelines are a new type of Vulkan graphics pipeline that provide a significant amount of assistance to the developer for managing and processing rays and enabling efficient batched ray processing under the covers. Ray queries are simpler and enable any Vulkan shader to manually launch a ray at any time and to process the resulting intersection data however it wishes. Let's first look at ray tracing pipelines, which enable the developer to compile and manage a set of shaders to handle any desired type of ray and material processing. The application then launches a grid of rays into the scene contained in the acceleration structure. For each ray, a particular shader will then be executed depending on what the ray intersects with, to process the desired type of visual effect. Hit shaders can query the materials that the ray has touched, for example, to process transparent materials differently to those which are opaque. Hit shaders can also control how additional rays are used to calculate effects such as reflections and refractions. There are also some special shaders that will execute if the ray is at its closest intersection to the eye, or if no hits occur at all for that ray, which can be used to render the sky in an outdoor scene, for example. The second technique, which Vulkan calls ray queries, enables the application to explicitly fire single rays from any type of shader and also use that shader to process the returned intersection data. Shaders can also control how traversal proceeds through the scene in the acceleration structure, enabling the application with significant flexibility to use rays really however it wishes. A typical ray tracing application can use hundreds or even thousands of shaders to process the many types of visual effects in a scene. Compiling that many shaders into a ray tracing pipeline can be intensive enough to cause application stuttering when new scenes are loaded or when new scene effects are needed. It can be particularly aggravating to discover that a scene suddenly needs a new shader, and that triggers the entire set of shaders for that scene to be recompiled and reloaded. To avoid that overhead, the Vulkan pipeline library extension enables a library of SPIR-V shaders to be incrementally compiled into an existing ray tracing pipeline, saving the need to recompile everything from scratch. Now, pipeline libraries can be helpful when dynamically managing the shaders in a scene, but there is still significant setup processing for any ray tracing application, and it's not just compiling shaders, but also loading the scene geometry into acceleration structures. To help applications use all available processes in a setup processing, Vulkan enables host CPU to build acceleration structures in host memory for subsequent download to the GPU, in parallel with the GPU rendering. Also, Vulkan provides a general mechanism called deferred host operations, where the Vulkan driver returns a deferred work handle to the application for later execution. This enables the application to control work execution and to distribute work onto multiple cores and background threads. In a ray tracing application, for example, deferred host operations can be used to asynchronously use multiple CPU cores to build acceleration structures on the host. Now, an industry trend that is significantly influencing Vulkan's ongoing design is the increasing use of Vulkan as a porting target to accelerate layered implementations of other APIs. This enables an application using an API such as DirectX 12 to be deployed on systems where native DX12 drivers are not available, such as Linux. This is becoming a widely used and proven technique as Vulkan is designed to be an effective layering target, and the open source compiler ecosystem leveraging SPIR-V becomes increasingly robust. For example, the VKD3D open source project layers DX12 over Vulkan and is used by Valve and other developers to enable DX12 games on Linux. As ray tracing in games becomes widely used, VKD3D will need to layer DirectX 12 ray tracing functionality over Vulkan. And this has resulted in Vulkan ray tracing being designed to be used by layered APIs as well as directly being used by developers. Another important part of enabling layering of DXR over Vulkan ray tracing is the use of HLSL ray tracing shaders in Vulkan. Khronos has already been working closely with Microsoft over the last few years to integrate a SPIR-V backend into Microsoft's open source HLSL compiler, which is called DXC. This has given Vulkan developers the choice of using either GLSL or HLSL shaders in their Vulkan applications. With the release of Vulkan ray tracing, NVIDIA has added code generation to DXC to generate SPIR-V when using the Vulkan ray tracing extensions from HLSL. As well as enabling layering, developers can easily port their ray tracing applications between DX12 and Vulkan with minimal changes to their HLSL shaders. So how do Vulkan ray tracing and DX12 DXR compare? The good news is that the two APIs share the same fundamental architecture, which makes it relatively straightforward to port code between the two. Both APIs have ray tracing pipelines, and with the recently announced DXR Tier 1.1 launched as part of DX12 Ultimate, DXR introduced inline ray tracing, which is the equivalent of Vulkan ray queries. DXR Tier 1.1 also introduced the incremental addition of shaders to a pipeline, similar to Vulkan pipeline libraries. Vulkan is currently unique, though, in supporting host building of acceleration structures, together with deferred host operations. And Vulkan also has hooks for supporting cross-vendor debug tools, such as RenderDoc. Even though Vulkan ray tracing was just released at the end of 2020, diverse applications are already beginning to ship using these new extensions. The world's first cross-platform ray tracing application was Quake 2 RTX, where NVIDIA integrated advanced ray traced effects into this Vulkan port of a gaming classic and made the source code openly available. And there are many more games using Vulkan ray tracing in development. Holochip has used Vulkan ray tracing to develop rendering techniques that render light fields as quickly as single views for devices such as the Looking Glass display. AI Motive has developed the world's first ISO 26262 certified automotive simulator that uses Vulkan ray tracing to compute physically realistic input for the sensors, including cameras, LiDAR, and radar, as well as the realistic rendering. And finally, Industrial Light and Magic has integrated Vulkan ray tracing into their Helios render to enable the display of movie visual effects displayed on studio LED walls while scenes are being shot in real time. Before I finish, I would like to introduce Khronos' newest working group that was announced at the beginning of March 2020. Inari is defining an API for analytic rendering or scientific visualization, which often uses ray tracing. Inari, though, is at a very different level than Vulkan. It gives scientific visualization applications a portable cross-vendor API into high-level renderers such as NVIDIA's VisRTX or Intel's Osprey. Those renderers in turn call down into low-level acceleration APIs such as Vulkan. Applications using Inari will be able to simply provide data describing objects in a scene and let the renderer take care of all the rendering mechanics. If your company is building renderers and you may want to expose that rendering functionality through a higher level API such as Inari, please consider getting involved. to ensure this new API meets your needs. So I hope that was a useful update on Vulkan ray tracing. You can download Vulkan ray tracing drivers from AMD and NVIDIA today, with Intel support coming soon. We have also compiled a list of resources here, including samples, guides, and tutorials to help you easily use ray tracing with Vulkan in your applications. All these resources and more are available on the Khronos website at www.khronos.org. Thank you.